All right, this is the second hour of Physics 1C for September 22nd, and we're now going to say something about equipotential lines and how they compare, or what they would mean for gravity, basically. Because we learned about gravity in previous semesters, and you didn't learn about equipotentials. So let's say something about how equipotential lines are similar to gravity. So let's start off by saying that I have like a hill. Like this. Right? And I want to come up with something that is similar to this idea of voltage, okay, the idea of potentials, okay? So if I think about different points along here, let's say that this top of this object right here is 5 meters, okay? And I label off where 4 meters is, 3 meters, 2 meters, and 1 meter. And then obviously 0 at the bottom. What I can say is that for each of those, if I draw a line from here to here, make it straight, and then put a line for every one of my elevations. Oops. So I draw a line for every one of my elevations. Then each one of these elevations is going to be basically an equipotential for gravity, okay? So we say this is y equal to 5 meters, right? This is y equal to 4 meters, and so on and so forth. These lines right here, okay, are a line along which the potential is equal to, or the elevation, we'll just say the elevation is similar to, or corresponds to, electric potential lines, okay? And objects, obviously, if I take an object that's like a piece of mass and I place it right here, the mass will always move to lower and lower and lower elevations, right? So in order to describe how this would work on, let's say, a flat map, what you can do is you can draw elevations on a map by drawing lines along which the elevation is the same. So on this picture right here, if you trace out one of these lines, like this line right here that goes around in a circle like this, not a circle, but it's a closed path, right? Each one of those lines represents an elevation. Okay? You can see what the elevation is in some cases. For example, this line is 700. And this line is 900. And in between you have some kind of steps, okay? But the idea is that every one of those lines represents a constant elevation. So let's see if you understand. If I were to take a ball on my map right here and I placed it right here, what direction would it roll? Would it roll that way? Would it roll this way? Would it roll up and to the left? Would it roll down and to the right? What direction would a ball placed at this location low, do you think? You can kind of tell because of the way that the map is like three-dimensional somewhat. Actually, maybe a better spot, an even better spot. This is a way better spot. What about if I placed a ball right here? What direction do you think it would go? Oh, I can't even see your answers. You're probably seeing answers. You all said correctly. Down to the right, down, down. Yeah. You know it's going to flow from a high elevation to a low elevation, right? From a higher elevation to a lower elevation. It appears that this line right here is something like 800. The lines beneath it are going to be below 800. The lines above it. Yeah, okay. And what do you notice about regions like this right here? Between this point and this point right here, what do you notice about this region and this region right here? Compared to, for example, over here, where the lines are really close together. What does it mean that the line here is really far away from this line and the other lines are really close together? What does that mean? Lines close together, what does that represent? Is that a rapid elevation change or is it a smooth elevation change? Rapid, right? So we know that this hill is really steep, right? That's a steep hill. But right here, we know that there's almost like a plateau between these 2 points, right? Now, there actually is a hill, right? Because this is a different elevation than this right here. But it's much more gradual in terms of the elevation change than the place where the lines are close together. When the lines get close together, that means that it's a really steep slope, right? Anyway, so we call these topographical lines. And topographical lines are very similar to equipotentials. equipotential lines. Have you all seen these kind of maps before? I put it on here because I think in the past people often say they haven't seen these kind of maps. Maybe some of you have, maybe some of you haven't. But again, it's a way to take a two-dimensional surface and be able to represent elevation change, which can be really important if, for example, you're going hiking, for example, and you want to find a trail where you don't have to go too far up or too far down. Or maybe sometimes you want to go on a trail where you do have a big elevation change so you can get some good exercise. Either way, topographical lines, equipotential lines are very similar. It makes sense that you would talk about this in 220 for sure. And I hope that when you think of equipotentials, it helps you to think about this idea of topographical lines. I don't know if it will or not, but I will say this much. This is the easiest thing to think about when you're thinking about what is potential. Think about potential as being like a height. If you think about that, I think you'll understand more about like what it is exactly. All right, now let's see if you all can figure this one out. Now, when I'm drawing in 2 dimensions, you get equipotential lines, right? But the reality is that there's technically a surface that comes out of the page, okay, along which the electric potential would all be 100 volts, okay? Because if our electric field is 3-dimensional, right, like if I can draw those same electric field lines like a meter in front and another meter, and if I can draw those electric potential lines coming in and out of the page, then I can also draw the equipotential lines like this. So if the field lines can be drawn to come out like this, we can make the equipotential lines create a surface. So equipotential lines are technically equipotential surfaces. They just become lines when you draw them on a 2-dimensional surface. So let's consider this quick quiz right here. So we have 4 different equipotential surfaces, okay? All along the bottom surface, the equipotential is 6 volts. The next surface is 7 volts. That's this surface here, little sheet. Then you have 8 volts, and then you have 9 volts. So what I want you all to do, I want everyone to do this. It says the labeled points in figure 25.4 are on a series of equipotential surfaces associated with an electric field. We want to rank from greatest to smallest the work done by the electric field on a positively charged particle that moves from A to B, B to C, C to D, D to E. I'll just put up here the definition real quickly here that the work done is going to be equal to, we said before it was like some QED, but this only really works for uniform fields. So what we know is that it's equal to the negative change in potential energy. Let me show you another relationship that we can use here. We also defined the change in potential energy divided by the charge to be equal to the change in volts, the change in potential, which means we can rewrite this to be that delta U is equal to Q times delta V. So writing it like this, then work would be equal to negative of Q times the change in potential energy, or change in potential. This is probably the equation you're going to want to think of when you think about this right here. Or you can think about it just conceptually, either way. We want to find not the change in potential, but the work done by the electric field. And I'm telling you the work done by the electric field is equal to the negative of Q times delta V. On a positively charged particle, so we know Q is positive in this problem, that moves from A to B, B to C, C to D, D to E. So of these motions, which one I want you to rank from greatest to least the work done by the electric field? Can you all do that? Type your answer in chat, but don't push enter. Okay, so type your answer into chat, but don't push enter. I'll give you a couple minutes to try to answer that. I'm sorry, I took the picture away. I'm so sorry, Justin. Thank you. Yeah, just put your answer into the chat, and don't push enter yet. Just wait until everybody has their answers. Okay, I hope that was enough time. So go ahead and push enter now. I guess I can type my answers in here too. That's what I got. I think other people said they got similar things. A to C and B to C are the same, right? So whatever order you want to write those in is fine. And then C to D, and then A to B, then D to E. Oh, there's only 4 of them. How did I do 5? Which one did I do that doesn't count? A to B counts. A to C wasn't one of them? Okay. Thank you. That makes sense why you all didn't have that one. I was like, why am I the only one that has this one? Okay, cool. So B to C, C to D, A to D, D to E. Looks like everybody got it right. Maybe some typos, but it does look like everybody's pretty much on the same page. Okay, so yeah, just writing the values of what you get for these is just to kind of quickly do this. From A to B, you're staying on the same sheet, which means that the change is 0. So I'm just going to write delta V here. Delta V is 0 from A to B. For B to C, you're going from B, which is 9, to C, which is 7. So you do delta V is going to be equal to -2. Actually, that doesn't help because we need the negative of delta V. So it's like, I don't know. You put a negative sign here. Negative delta V for this one is positive 2 volts. And then from C to D, you're going from here to here. So then negative change of potential difference here is going to be positive 1. And then from D to E, it's -1, right? You're going from 6 to 7. Anyway, just a little quick quiz to get you to think about how potentials work. Now we're gonna, I think, do a calculation real quick that we can do. Can't do these yet. We could do this one actually. Can't really do this one yet, but we can do this one. All right, let's do a quick problem here to show you how we actually apply this in problems. Okay, so it says a proton is released from rest at point A in a uniform electric field that has a magnitude of 8 × 10⁴ volts per meter. The proton undergoes a displacement of d equal to 0.5 meters to the point B in the direction of E. This may look similar to a homework problem from your first homework. We want to find the speed of the proton after completing the displacement. Okay, so proton moves from point A to point B. It starts off from rest, right? Yep, it says right there, VA is equal to 0. We have our uniform field between these two plates, and we know what the magnitude of the electric field is. It's given as 8 × 10⁴ volts per meter. We know the distance between these points is 0.5 meters. And that's it. We want to find what VB is equal to. What's the velocity at this point? Okay. So in order to do this, I'm going to use 2 of the equations that we derived, or 1 of the equations that we derived earlier. The first one we're going to use is that when you have a uniform field, we know that the electric potential difference is equal to -E times D. Okay? That's what the value of it is. We have E, we have D, we can calculate what this is equal to, right? The other equation that I'm going to use is from Physics 1A. The energy equation, which says that the work done by non-conservative forces, let's actually write the real equation. It says that the work done by non-conservative forces is equal to the change in kinetic energy of the system plus the change in potential energy. In this case, the only force that's acting is the electric force. The electric force is a conservative force, so we have the left-hand side equal to 0. Change in kinetic energy is 1/2 mass times final velocity squared, which is VB squared, minus V initial, or velocity at A squared. And this should be equal to delta U. Now, the other equation that we're going to use in this problem is the definition of what electric potential energy is. So for delta U, we're simply going to replace this with Q multiplied by delta V. And when we do this, you're going to put the actual sign of the charge into this equation here. So we're just going to rewrite, instead of delta U, I'm just going to write Q times delta V. In my opinion, this is the simplest way to do these type of problems, is just always replace delta U with Q delta V, okay? Always just do that. All right, so we've got our two equations. We now want to solve for VB. We know in this particular problem that VA is equal to 0, so we can make that equal to 0. And our goal is to solve for VB, so rearranging, what we're going to get is so do a little algebra and see if you agree that's what you get. Does it seem right? Okay. Now we have a negative sign here, which you might be thinking, okay, square root of negative, like maybe that's a problem. But, you know, when I plug in for delta V now, what we see is that that goes away, because now it's going to be negative 2Q times delta V is negative ED, negative ed, over m, and now those negative signs have canceled out. So we get that the velocity is equal to the square root of 2. Now we need the Q. What's Q going to be? How do I figure out Q? It's a proton, right? And the charge of a proton is about 1.6 times 10 to the negative 19 coulombs. We're also going to need the mass. The mass of a proton, this is also something you can look up, is about 1.67 times 10 to the negative 27 kilograms. Plugging all that information in, I don't know if we have enough room over here. We'll try 1.6 times 10 to the negative 19 coulomb times. All right, there's an E, which was 8 times 10 to the 4. So tilting. D is 0.5. And the mass is this. Okay, can you all calculate what that is for me? You'll get an answer? Yeah, that's what I got too. It's pretty easy, right? hope you think that's easy. I know that there's these new ideas that we're introducing, but ultimately, this is just an energy problem, and we now have a new type of energy, right? Delta U, that's equal to Q delta V. And that's really all that's different now, right? That's really the only thing that's different from a problem where, for example, you just try to figure out the velocity of a ball as it fell down or something like that, right? That's the only thing that's really different right there. So we'll do things that are a little harder than this, but you know, the key thing to understand is just this relationship. Now, finding what the potential difference is, that may be challenging in certain problems, but we'll learn how to do that too. And ultimately, this isn't that difficult. You have a question? I heard someone cue their mic. Did you have a question? Yep, delta V is going to be V final minus V initial. That's right. Yes. All right, what is next? I think next we talk about point charges. We did... Oh, I guess I could talk about electron volts real quick. Let's do that real quick. I mentioned this in one of the two lab sections, but I didn't mention it in the other section. So, since we know that Q times V is our definition for electric potential energy, we know then that if we take, for example, Q equal to E, where E is the same as it was in the previous problem, 1.6 times 10 to the minus 19 coulombs, then we can come up with a new measurement of energy, which is going to be the electron volts. So 1 electron volt corresponds to 1.6 times 10 to the negative 19 coulombs times volts, but a coulomb times a volt is just equal to a joule. So 1 electron volt has this value. You will definitely see electron volts show up in your labs. You'll also see them show up in some of your homework problems. It's just another unit that we use that is very useful to us when we're talking about really small objects. In fact, I wonder if we could have used it in this problem. I think we can. Just to show you how this would work, I just want to show you something here. I think this is kind of cool. You all probably won't think it's very cool, but that's okay. So there's other ways to measure some of these things. How would you do this one with electron volts? I thought I would, let's see. Maybe this is a bad example. We can measure mass in electron volts. This problem isn't particularly useful for this, so... yeah, it's not particularly useful in this case. Should I give up so quickly? Am I wrong? Let me see. You'd have to measure this in electron volts. I don't think it's particular. This isn't a particularly useful problem to talk about this with, but if I think of one where we can use it, I will. Anyway, something to know what it is. It's a unit of joule. It's a unit of energy, not a unit of electricity. It's just a unit of energy. It's the amount of energy you get when you accelerate a proton or an electron through 1 volt. Okay, so let's talk about point charges. So up till now, I just want to mention that this equation only works for E uniform. Okay, it has to be, or constant, whatever you want to call it. Okay, if we want to talk about non-uniform electric fields, then we have to use the definition of work, where it's F dot dr. Okay, and we have to replace inside our definition here the integral. We put in here Q times E for the electric force. And then what we do is we say, okay, we know that delta U is equal to negative of the work, which means that change in potential energy now has to be equal to the negative of this integral. Are you providing us these constants in the exam? Yes. I feel like I've answered that question multiple times. I guess what I've answered before is, will you have an exam? Will you have an equation sheet? You'll have an equation sheet. You'll get the constants, yes. Should you memorize them? Definitely. You should still memorize everything. It's just really helpful to memorize things. Regardless if you all think so or not, you absolutely should memorize things. The seconds. Like for the answer here, how do we get seconds? So to get seconds out of that, we have... Let's look at the units. So we have coulombs times volts over meters times meters over what? kg, which is equal to, so a coulomb, a volt we said was a joule per meter, a volt is a joule per coulomb. These meters cancel. And this is equal to joule per kilogram. I forgot to mention that we're square rooting all of this. What's a joule? A joule is a kilogram meters squared over seconds squared over kilogram. You square root that and you get meters per second. Does that make sense, Brandon? Always try it out yourself before you ask. You know what I mean? If you try it out yourself and it doesn't work, then you should ask. But it's always the case that if the units over here have to be the same as the units over here, always good to check. And I don't mind ever doing it, but try it yourself first, because you learn something from trying this stuff. I know you're not super comfortable with what a volt is yet, but you're going to have to get comfortable with it. It's one of the best ways on an exam to check your work is to do this. I'm glad you brought that up. All right, so getting back to this. So we said that for a uniform field, you could just do delta V is equal to negative E times D. But for non-uniform electric fields, which is what most electric fields are, you have to go back to our definition of work due to a non-constant force, which is this. Replace the electric force with what we always replace it with, which is charge times electric field dot dr. We then say change in electric potential energy is equal to negative W. So we basically just pop a negative sign in there, put change in energy over here. Finally, we'll use the other expression that tells us that to get to electric potential difference, we have to take electric potential energy and we have to divide by Q. So if we divide the Q to both sides here, so we just basically divide both sides by Q, then this will become delta V. And we can say that delta V is then going to be equal to the negative of the integral of E dot dr. This is a line integral. It's a line integral, which you probably studied in 220, right? I think line integrals are something you study in 220. You find, you do like mass density functions and you find the weight of a line, stuff like that. Right? Am I crazy? You do, right? You do line integrals? And okay. Some of you are taking 220 right now. Maybe this is what you're doing right now. I think it's one of the earlier things that you learn about, right? All right. Now, if you took Physics 1A, you've also... Oh, it comes later on? Okay. Well, that's how it goes. We start Physics 1C off. We do some integrals that you're familiar with, right? And then we jump into Gauss's law, where you have triple integrals. You're doing volume integrals, right? And now we're doing line integrals. We've covered a lot of vector calculus all in the first month. This is why people think the beginning of this course is so hard, I think. Is because we throw all this math at you, you get overwhelmed, but then the reality is you go do the homework problems and you don't actually have to do a lot of that vector calculus stuff, right? You don't have to do a lot of that vector calculus stuff. I mean, yeah, you have to learn how to find, like, some things, but a lot of times you don't actually have to do it. And that's what we're going to see today. So this equation is our general definition of the electric potential difference between 2 points, and it has this negative sign here. Now, I believe your book writes this in a slightly different way, okay? For me, say we were going between some point A and some point B, so I labeled this as point A and point B. I would write this as VB minus VA is equal to the negative of the integral of A from A to B of E dot dr, okay? This would tell us if I take VB minus VA, I do the integral from A to B, and I get a negative sign, right? Your book, what your book has instead, what it says is, it writes this as V, how does it do it? I can't even remember. It's so weird the way that it does it. I believe it writes it as VAB is equal to VA minus VB. We're actually going to check after I write this to see if I'm right or wrong about this. Is equal to the integral of, it's the same integral. They don't change the integral. So some textbooks write it like this. Your textbook writes it like this. I'm just going to verify real quick because I don't want to throw you completely off because I don't have their notation memorized very well. Yeah, right there. I think I got it right? Well, kind of. Maybe it's the previous page. There we go. Right there. There we go. Okay. All right. So this is the book's version of this right here. In fact, you know what I'm going to do? I'm going to put it in the notes just so that we have it, because I want you all to... I want you to know what they mean when they write what they write. But this one doesn't have it written like that, though. We need two of them. So we're going to need that one. So that's one of their definitions. The other piece that you're going to need to know for when they ask questions in the text is... Oh, here it is. It's right here. It's kind of hidden. Ah, this book is so annoying. It's hidden right here. So again, I'm just going to print screen, paste it. I'm just going to use their exactly what they say. I don't want to have any chance of copying it down wrong. All right, now let's see if I got it right. Oops. It's not super important that I get it right. Did I write it right? VAB is defined as VA minus VB. That's correct. And for them, VA minus VB is equal to integral from A to B of E dot DL. Yes. Okay, now look at these two equations. Do they look the same to you? So for me, I'm always going to use this type of notation. I'm just going to say this is delta V. They call it VAB. They both, do you all agree they both say the same thing? Yeah, it's the same equation. All they did was just to confuse you, they changed the order of this. And that's enough to make it so the negative sign goes away. I guess they don't want the negative sign in the equation. I like the negative sign being there, because ultimately, what does this all go back to? It goes back to this relationship right here. That negative sign needs to be there. We want the negative sign to be there, because we want downhill to be going from high voltage to low voltage, right? And if we want to have downhill be high voltage to low voltage, you have to have the negative sign there. All right, so we've got our equation, and in order to understand how this works, we need to apply it to a situation. If you all have questions, please feel free to keep asking. But keep in mind, when your book says VAB, they mean this, which is the same thing as this. They're 100% the same thing. It's just they choose to write it in it's a very unique way. Maybe it's a good way. I don't really know. But all right, so let's look at an example of a non-uniform field, and let's find the electric potential in that situation. So the easiest one to use is a point charge. What's up? Question? Can we cover all of lectures today? What does that mean exactly? Are we going to get to all the topics, you mean? Probably. Yeah, I think so. All right, so we have a charge Q, and we're going to calculate the electric potential, not by using that equation. We're going to use my equation. I like it better. We're going to use that equation. We're going to find the electric field for a point charge. So here we have a point charge. Do I need to draw the electric field lines for it? I guess I could. It doesn't hurt. So the electric field lines for this point charge are going to kind of point out radial away from it, as you all know. Okay, so if these are the electric field lines, and they go all around, I'm not going to draw all of them. So these are our electric field lines. And I want to figure out what the electric potential difference is at 2 points on my graph. So for example, suppose that we move from this point here to this point right here, and I call this point A, and I call this point B. I want to figure out the work done by the electric field if I try to move a point charge from this location to this location. So this one is fixed. This charge is fixed in place, and I want to find the electric potential difference between these 2 points right here, okay? VB minus VA. All right. So it says I need to take the electric field dot product with the displacement. The electric field for a point charge we found in the past was equal to K, the electric constant, times the charge divided by the distance away from the charge squared, and then multiplied by r hat, right? And I'm just going to tell you here, just to kind of help you out with this, dr, we can think of dr in multiple ways, but one way we can think about it is you can write dr as something like dx I hat plus dy j hat plus dz k hat. Okay, that's one way that you can do it. Or sometimes if our r already shows up in the problem, like it does in this case, we might not even have to do it. All right, so let's draw. Do I need to? Yeah, I need to draw some lines in here. So we're going to move this object from this point here up to this point here. And I'm just going to make them kind of separate. I'm going to label this as r sub A, and I'm going to label this one as r sub B. Okay? Each of those vectors there. And then we're going to go ahead and start to figure out what this is. So delta V is equal to the integral from A to B. I'm going to write this as the integral from r sub A to r sub B of E dot dr. E is KQ over r squared, r hat, dot product with dr. What is dr? So dr is going to be like a little change in displacement in this direction, okay? Which means that if r hat is a vector that points in the r direction, these two are parallel to each other, which means that r hat dot dr is just going to be equal to the change in radius dr. If we plug that into our equation, ooh, I left something out. There's a negative sign here, right? Negative sign. Okay, so negative, I'm going to pull the constants out. KQ integral r sub A to r sub B of what's left? Just 1 over r squared dr. What is the 1 over r squared dr? What's that going to be? If I take the integral of 1 over r squared dr, what do I get? Natural log, sine, cosine, what do you get? Negative 1 over r, seems right. So this is equal to negative KQ times negative 1 over r, evaluated from r sub A to r sub B. Why does r hat dot dr equal dr? Okay, so r hat would be a vector that points this way, right? And dr is a vector that points in the same direction, right? I'm drawing it off to the side, but does this make sense that r hat and dr, they point in the same direction? So when I write down what r hat dot dr is, this would be equal to the magnitude of r hat multiplied by dr, but again, I just need the magnitude of this, multiplied by the cosine of the angle between the two of them. If r hat points this way and dr also points this way, the angle between them is 0. The magnitude of r hat, it's a unit vector, so it has length 1. Dr, magnitude of dr is just, this by definition is just d with a little r like this. And then you multiply by 1 again, so you get dr basically. Yeah, no problem. Okay, so we have negative KQ times negative 1 over r, RA to RB. This should all be equal to the change of potential between those 2 points. So we have delta V now is equal to, the negative signs cancel out, so we end up getting KQ over RB minus KQ over RA. So that's the potential difference between those 2 points. But we said before, as you can see up here, that the potential is VB minus VA. So if we compare these, we know that the potential at point B is equal to KQ over R sub B, and that's the potential at B. And the potential at point A is defined then as KQ over RA. Which means in general, we can say that for a point charge, let's write this in a different color. For a point charge that's fixed in place, the electric potential is equal to KQ over R. It's a scalar too, so you don't need any vectors or anything like that. There we go. That's the electric potential for a point charge. It's a pretty simple relationship. Can you all see how we got there and why that makes sense? We started from this equation. We plugged in the electric fields. We plugged in our limits. We evaluated the integral. We got down, this is our answer. 1 over R. So just as a way to think about this, now that we know what that is, suppose that I take a positive charge that has 9 nanocoulombs, okay? So I pick let Q equal to 9 nanocoulombs, right? Now, suppose that I come to a few different distances here. So I go 1 meter, 3 meters, and I want to calculate what is the potential at this location, we'll call it V1, and I want to find what is the potential at this location, we'll call it V2. Okay, 1 meter away, 3 meters away, okay? According to my definition right here, V1 would be equal to K, which is 9 times 10 to the 9, times Q, which is 9 times 10 to the negative 9 coulombs. And we would divide by the distance, which is 1 meter. You don't square it in this case, you just divide by 1. So we're going to get, what is that, 81 volts, right? This is 81 volts. Okay. What about V2? V2 will be equal to all the same stuff, but we divide by 3. So we're going to get 9 times 9 is 27. You divide by 3, you get 9 volts. So at this location right here, the voltage is 9 volts, right? 81 volts, 9 volts. What about the equipotential lines? Well, if I have a positive charge, the equipotential lines are circles. Circles. Because those are the places where R is a constant, and again, the potential is KQ divided by R. Does that make sense? When you have multiple point charges, so if you have multiple charges, let's say you have n point charges, than the total electric potential you get by just adding up all the individual electric potentials. So just as a simple example of this, if I have a point charge right here, and I tell you that it's 3 nanocoulombs, and I have a point charge over here, and let's say this is Q1, let's say this is Q2, and let's say that this charge is, I don't know, like -5 nanocoulombs, okay? And I want to figure out, like, let's say I come to a position, I don't know, somewhere in the middle. It's fine, I guess. And let's say that the distance between this point and this point is 2 meters. And the distance between this point and this point is 1 meter. And I want to figure out what is the electric potential at that location. Then all you have to do is you just add up the individual electric potentials. I'm getting slammed with emails right now. It's so frustrating. I have to close this tab. I can't take it anymore. It's so frustrating. Okay, this is right here. All right, so the total potential is going to be the sum of the individual potentials for each of these particles. So if I have Q1 at 3 nanocoulombs and Q2 at -5 nanocoulombs, and I want to know right at this point, which is 2 meters away from the 3 and 1 meter away from the -5, what is the electric potential right here? And all you have to do is you just take KQ1 divided by, let's call this R1, let's call this R2, plus KQ2 divided by R2. And then when you plug the numbers in, you leave the signs as they are. So it'll be 9 times 10 to the -9. This is Newton meter squared over Coulomb squared. This multiplied by Q1 over R1, so 3 times, sorry, this is positive, 3 times 10 to the -9 coulombs divided by R1, which is 2 meters. I still hear someone breathing. It is so frustrating to sit here and listen to you breathe while I try to talk. It's really distracting. Please make it so that you don't accidentally cue your mic. No offense to whoever that happens to be. Q2 is -5 nanocoulombs, so you put the -5 in here. And then you divide by the distance, which in this case is 1 meter. And that'll give you the electric potential at that location. So if we do that, we get, well, this is easy to do, because it's 3 over 2 minus 5, which is going to be, I think, -3.5. I'll calculate it just in case, but I think that's what you're going to get. No, that's not right. It's times 9. So it's whatever 3.5 times 9 is. So -31.5 is what I get. If the middle point is the point charge, we'll have a different answer. Do you mean if I add another point charge in here, will you get another answer? Is that what you're asking? Yeah, of course. If I add more points onto here, it will definitely change the answer. But every one that you add, you just add another term, right? That's all you got to do. It's really easy. In fact, it's much easier than what we've done in the past because we don't have to have vectors anymore now, right? Like if we wanted to find the electric field due to these two charges, we'd have to draw vectors in here, right? But we don't have to do that anymore. We don't have to. It's not needed. Now, one thing that I've left out of all of this is if we go back a little bit to the way we were talking about this originally, come back to, where was it? The uniform field thing, this right here. Remember that what we did to figure out, we called this 100 volts, 90, 80, 70, 60, 50, right? For things that are, equally separated apart, where the electric field we defined to be 10 volts per meter up here, right? Now, notice that when we did these calculations here, I said that delta V between 1 and 4 was 30, delta V between 1 and 2 was 10, -10, and from 0 to 1 was -10. And I said, let's just pick 100 volts to be this point right here, because I knew that they'd make it 100, 90, 80, 70, 60, 50. It's a pretty easy way to think about it, right? But I told you, you could have picked whatever you wanted for this. So when we're talking about point charges, the usual thing to do is to make the electric potential equal to 0 at infinity, okay? Because of the definition of how we've defined this, okay, this answer is, we are assuming that V is equal to 0 at an infinite distance away. As r goes to infinity, V goes to 0. And hopefully that makes sense, because if you look at the definition of the equation, V equal to KQ divided by R, when r goes to infinity, V naturally goes to 0. So this is a choice that we make. We usually assume that the electric potential is 0 at infinity. Does that make sense? Okay. Now, I have, I believe, 1 or 2 more problems that I want to do. This one. Definitely want to do those 2. I definitely want to do this one. I'm pretty sure we can do those after the break. Unless I want to do one of them really quickly, and I don't think I do. I mean, we might be able to do this one really quickly, but I think it's a good idea to just take a break and then put some time into solving these. So I'll leave you with this. We'll take a break for 10 minutes, and then we will come back. So that'll be 24. So 3:24. Okay, stopping the recording.